Our next topic in surface chemistry is adsorption isotherms. Adsorption isotherms. Iso means constant, therm means temperature. Temperature is constant here. The variation of amount of gas adsorbed on the adsorbent with pressure at constant temperature. When amount of gas adsorbed on the adsorbent with pressure at constant temperature can be expressed. It can be expressed by means of a curve. That curve is called adsorption isotherm. And we have to study Freundlich adsorption isotherm. Freundlich adsorption isotherm. This gives a relationship between the quantity of gas adsorbed on unit mass of solid adsorbent. This adsorption isotherm gives the relationship between the quantity of gas adsorbed on unit mass of solid adsorbent and pressure. The relationship is between the pressure and the amount of gas adsorbed on unit mass of solid adsorbent at constant temperature. Now for this relationship, let's say X is the amount of adsorbate. This is the amount of adsorbate we are taking. And let's say M is amount of adsorbent. So X by M will be extent of adsorption. How much adsorbate can adsorbed on unit mass of adsorbent, which is called extent of adsorption. So in this curve we are taking X by M on one side, that is we are taking extent of adsorption and its relationship with the pressure we have to study by taking the temperature constant. So the graph will be like this, a straight line graph at low pressure, little curved graph at intermediate pressure, and at high pressure this almost becomes constant. And this point, this pressure, where extent of adsorption is almost constant, this pressure is known as saturation pressure, denoted by PS, called saturation pressure. Now from this graph, at low pressure what we see is a straight line graph. Straight line graph denotes that extent of adsorption is directly proportional to pressure when pressure is low. X by M, if we remove the sign of proportionality, we'll get a constant. Now at high pressure what we observe at high pressure is that extent of adsorption is constant. So at high pressure, X by M is proportional to P naught. P naught is independent of pressure. Remove the sign of proportionality. Again a constant will come here and P naught. Now at intermediate pressure, since we are getting a slightly curved graph here, this curve is slightly curved here, so at intermediate pressure, extent of adsorption is proportional to P raised to power 1 by N. It is X by M is proportional to P raised to power 1 by N. That is, X by M will depend on pressure raised to the powers between 1 and 0. That is the fractional value. So X by M equal to a constant. This constant we are taking K. P raised to power 1 by N, where N is a positive integer. N is a positive integer and K is constant. K is constant. Now to check the validity of this equation, to check the validity of this equation, we are taking the logarithm on both sides of this equation 1. So when we take logarithm on both the sides, we get log X by M equal to log K plus 1 by N log P. And now if we plot a graph between log P and this side now we're taking is log X by M. Log X by M and log P. Then we'll get this kind of curve, that is a graph between log X by M and P is a straight line graph. If it is a straight line graph with slope equal to 1 by N, the slope is equal to 1 by N and intercept is equal to log K. Intercept is equal to log K. So slope is equal to 1 by N and this intercept is equal to log K. Slope is equal to 1 by N and this intercept here is equal to log K. Limitations of Freundlich adsorption isotherm. It holds good over a limited range of pressure. Only for a limited range of pressure we can use Freundlich isotherm to see the relationship between the extent of adsorption and the pressure. Our next topic after Freundlich adsorption isotherm is applications of adsorption. Applications of adsorption, where adsorption phenomenon can be used. Number 1, in production of high vacuum. In production of high vacuum, adsorption phenomenon is used. How? If traces of air, if some amount of air is left in a vessel and we want to remove that also, then in that vessel charcoal is added. What is added? Charcoal. This charcoal will adsorb all the left air in a vessel and hence evacuated that. So a high vacuum will be created. The traces of air which are left after removing air with the help of vacuum pump can be further removed by using a charcoal. Second application of adsorption, gas mass. In gas masks also adsorption phenomenon is used. The gas masks they have activated charcoal. They have activated charcoal or mixture of adsorbents. These adsorb the poisonous gases, harmful gases, and thus helps in breathing in coal mines. So the people who are working in coal mines, they can come in contact with poisonous gases. So they use a mask. In these masks, activated charcoal or mixture of adsorbent is packed, which will absorb all these poisonous gases, and in this way they help in breathing in coal mines. Next application, control of humidity. Control of humidity. How humidity can be controlled? For this, silica and aluminium, their gels are used as adsorbents. They are used as adsorbents for removing moisture and thus controls humidity. Like the water flask that we buy from the market, it has a small packet inside which has silica gel. So if that flask will come in contact with humidity, it will not get spoiled because the silica gel packed here will absorb all the moisture inside that flask. Next application, removal of coloring matter, the colored material from solution. If we want to remove that colored material from the solution, then animal charcoal is used. This removes the colors of solution by adsorbing all the colored impurities in that solution. Like in case of sugar, to purify sugar, the brown impurities in sugar, they are removed by adding animal charcoal in it. That animal charcoal will absorb all these brown impurities and thus helps in purifying the sugar. Next application is in heterogeneous catalysis. Catalysis means a process in which a catalyst is used. A process is catalyzed by the use of a catalyst, that is, its speed increases with the use of this catalyst. And in case of heterogeneous catalysis, the physical state of reactants and the catalyst is different. Reactants and catalysts are not in the same physical state, then that catalysis is known as heterogeneous catalysis. So in this case, the reactants, they are not reacting with each other, or their speed is very less to react with each other. Then a catalyst is used. A catalyst is used here. This catalyst is solid. This is a catalyst which is in a solid state, and these are the two reactants. They are not reacting with each other, or their reactivity is very less. So a catalyst is added. These reactants, they adsorb on the surface of this catalyst. They adsorb on the surface of catalyst, and now the two can react with each other. So when reactants adsorb on the solid surface of the catalyst, the rate of reaction increases. So adsorption is helping the two reactants to react with each other easily. Example, in manufacturing of ammonia, nitrogen reacts with the hydrogen and this formation of ammonia. A catalyst iron is used to increase the speed of a reaction. Now next application of adsorption is in separation of inert gases. If you have a mixture of inert gases, how we can separate these gases from each other? Due to difference in the degree of adsorption of these gases by charcoal on the surface of charcoal, the degree of adsorption of inert gases is different. So using this concept, the inert gases can be separated from a mixture. So on the surface of charcoal, mixture of noble gases, they get adsorbed on the surface at different temperatures. At different temperature, different noble gases, they will get adsorbed, and in this way the mixture of inert gases can be separated out into its components. Next application is in curing diseases. In treatment of diseases, the drugs are used for the treatment of diseases. These drugs kill the germs of the diseases by getting adsorbed on the surface of the drugs. Suppose this is a drug and these are germs. These germs, they get adsorbed on the surface of drug and hence they are killed by this drug. So in curing of diseases, adsorption phenomenon is used. Next is froth flotation process. Froth flotation is used to concentrate the sulfide ores. In metallurgy, in sulfide ores, the gangue particles that we want to remove, that is, for concentrating sulfide ores, froth flotation phenomenon is used, and in this case pine oil is used. To sulfide ores mixture in water, pine oil is added, and on the pine oil the ore will stick and the gangue particles will remain in water. So the ore will go towards pine, while from the ore the gangue particles will remain in the solution. So from ore the gangue will separate out because ore will adsorb on the pine oil. So in this way the sulfide ores are concentrated using adsorption phenomenon. Next is in chromatographic analysis. In chromatographic analysis, chromatographic method is used to separate the components. And now if the components have the different adsorption powers, then by chromatographic technique these components can be separated out. Like we have done column chromatography. A burette is used here in which adsorbent is added, and adsorbent is packed here, like silica gel is packed here, and on the top of this adsorbent a mixture is added which we want to separate into its components. Now this will start moving in this adsorbent, and at different heights different components will get adsorbed because their adsorption powers are different. So at different heights they will get adsorbed. So in this way the mixture will separate out into its components using the phenomenon of adsorption. These are applications of adsorption. Now our next topic, a very small topic, adsorption Isobar. Adsorption, isobar. Now we have to study adsorption here by keeping the pressure constant. Bar means pressure, iso means constant. So in this way, in this process, we are keeping the pressure constant. So we have a plot here for physisorption and for chemisorption. A plot between extent of adsorption. Extent of adsorption is denoted by X by M. A plot is there between extent of adsorption and temperature, keeping the pressure constant. Pressure is constant. Now, in case of physisorption, as it is expected, we will have a curve like this. That is, adsorption is decreasing with increase in temperature. While in case of chemisorption, first extent of adsorption increases with increase in temperature, and then extent of adsorption decreases with further increase in temperature. In case of physisorption, it is expected only that when temperature will be increased, the adsorbate and adsorbent, the force of attraction between the two will break with this temperature. The heat in that temperature will break the bond between adsorbate and adsorbent, and hence adsorption will decrease with increase in temperature. But now a question is, why in chemisorption this initial increase in adsorption is there? Any chemical process, any chemical reaction, reactants, first of all, they have to be activated and then only they will react. And for activation of reactants, energy is required. They need activation energy. So initial temperature provides energy for reactants to get activated. So when reactants are activated, of course, the process will increase. So initial increase in adsorption is because of the fact that the heat supplied acts as activation energy required in chemisorption. Now further increase in temperature now will break the forces between adsorbate and adsorbent, and hence now adsorption will decrease with increase in temperature. Next topic after adsorption isobars is catalysis. Catalyst is a substance. Catalyst is a substance which influences the speed of a chemical reaction. It affects the speed of a chemical reaction without itself undergoing any chemical change. And is recovered as it is at the end of the reaction. And this phenomenon is known as catalysis. Catalysis is that substance which actually affects the speed of a chemical reaction, and itself it will not undergo any chemical change, and this process is called catalysis. Example, when potassium chlorate is heated strongly, it will decompose to form KCl and oxygen. It decomposes at a very high temperature of 853 to 873 Kelvin. But if this process is carried out in presence of a catalyst, manganese dioxide, then the process can take place at a low temperature of 473 to 633 Kelvin. So the catalyst increases the speed of a reaction, but itself it is not taking part in this chemical reaction. Next, promoters and poisons. Promoters are substances that increase the activity of a catalyst, while poisons decrease the activity of a catalyst. For example, in Haber's process of manufacturing of ammonia, this process is a Haber's process which is used to manufacture ammonia. Iron is a catalyst here, while molybdenum here is a promoter that increases the efficiency of this catalyst, while CO in this process is a poison. It is a poison. So if there will be CO here in this, then the activity of the catalyst will decrease. After knowing catalysis, the promoters and poison, we are coming to the two types of catalysis. Catalysis is classified into two groups, homogeneous and heterogeneous catalysis. In case of homogeneous catalysis, the catalyst is present in the same phase as that of the reactants. For example, if we take sulfur dioxide gas and reacts it with oxygen gas, this formation of sulfur trioxide gas. The catalyst used is NO gas. So the physical state of catalyst as well as that of the reactants is the same, then this is known as homogeneous catalysis. Another example is if we take ester, that's a liquid state, and to this if we add water, we get acetic acid liquid, plus we are getting methanol, which is also in a liquid state. Aqueous is a mixture. So the catalyst used here is liquid. So catalyst and the reactants here are in a same physical state, liquid state. So this is called homogeneous catalysis. Second is heterogeneous catalysis. When a catalyst is in different phase from that of reactants, the phenomenon is known as heterogeneous catalysis. Example, ammonia when reacts with oxygen, there is formation of NO and water. Ammonia is in a gaseous state, oxygen a gaseous state here, while the catalyst used in this process, platinum, is in a solid state. So this is an example of heterogeneous catalysis because physical state of catalyst and that of reactants is different. One more example, sulfur dioxide gas when is reacted with oxygen gas to form sulfur trioxide, like we have done it here also. But in place of NO, if we take vanadium pentaoxide as a catalyst here, then this is in solid state and reactants are in a gaseous state. Now this becomes the example of heterogeneous catalysis.